Hello and welcome to my class. Today I'm going to discuss the variable mass solution. And variable mass solution, the first example is rocket propulsion. Now in rocket, what happens when the rocket goes up and the fuel exhausted, and by the time it goes up, a lot of fuel just burn up and the mass reduces. As the mass reduces and velocity increases, and thus the mass is not constant in this case. In maximum time, what we discuss about the motion of different objects and their momentum and all that, in all those cases actually what happened, the mass is constant. For example, we talk about a body is moving from this point to that point. Suppose a body is here and is going to another point B, and here velocity is u and velocity is increases to v in another point. In this case we talk about the mass, and we suppose mass is m, and here momentum is m into u, and here momentum is m into v. In both the cases mass is constant. But in rocket propulsion, suppose I'm giving you another example. Suppose a motorbike, I made my tank full. The capacity of my motorcycle is actually 13 liter, and there will be certain mass of those 13 liter petrol. I'm going a long distance, I'm cruising in a long way, and after 1 hour, 2 hour, 3 hour, what will happen? A lot of amount of petrol will be burned. So after a certain distance, if 7 liter petrol is left behind, that means 5 liter petrol is burned. So mass of this 5 liter petrol will be reduced from my motorcycle. So mass is not constant, mass will be reduced. So in rocket the same thing happens. Now talking about the rocket, suppose this one is rocket and there is a full chamber full of fuel, and after a certain time this part is burned up, this part is gone. So mass reduces. Suppose this is initial mass m0 of this rocket. After certain time the mass reduces to m. Definitely m is less than m0. This is the case of variable mass. Now suppose initially the time was 0. When the time was 0, we take the mass to be 0. Time 0, mass not 0. Taking the mass is m0 or m0. This is the initial mass of the rocket when we are just counting the time. We have start counting the time, and this time is t equals to 0. Now after time t, the velocity changes when t equals to t. That means after some time, and that time is t, the mass changes to m and velocity changes to v. Initially the velocity was v naught. This was the initial velocity. This is the final velocity, or we can say after certain time the velocity changes to v when t equals to t. So these are the certain changes that takes place. Now we take an interval of time. Let us consider an interval of time as dt. This is a small time interval dt, and after this small interval of time dt, some mass reduces. How much mass reduces? That mass reduces to the reduction of mass is dm. This much of mass reduces. and by this reduction, when the process is going on, some velocity also increases, and that velocity is velocity increases dv. So this much velocity increases, this much mass decreases, and the time taken is t. And this gas existed from here, so there will be certain velocity of the gas. The gas is coming out from the rocket, and it also has certain velocity, and that velocity is vg. This is the gas which is coming out from the rocket, and its velocity is vg. So these are the certain information that we get or we consider at the initial state. Okay, take a pause and note down all this information in a notebook. Taken? Okay, I'm going to rub it. Very interesting, these things. Actually, in class 10, the concept of variable mass is not clear to us, but here we are actually thinking of the variable mass, and this is really practical, this is really interesting. I think in some sense this concept is new. Now, using the principle of conservation of linear momentum, we know in conservation of linear momentum, what happens, the total the momentum before and after. In case of collision, we can say the before collision and after collision. Now here the collision is not taken place, but the total momentum is conserved. Now the conserved momentum means when the mass is constant, the velocity changes, and here the velocity and also mass both are changing, but the concept is same, the momentum will be conserved. So some part going out with some momentum means when the rocket is going up, some part as gas coming down, so here will be some momentum and here will be some momentum, sum of this P1 and P2. Now when the process is going on, and after some time what happens, it is separated, actually some part gone with some momentum and some part left behind. So momentum of this portion and momentum the gas which is actually now separated from the rocket, though it is existed but it gone with some momentum, and that taking into account total momentum will be conserved. This simple line is okay, this is valid, the total momentum is conserved. So we can write from the conservation of momentum from the law of conservation of momentum, we can write, what can be written? It can be written after time t, when t equals to t, the mass was m and velocity was v. This momentum is actually m the part which is left behind, m minus dm. dm is decreasing, and similarly velocity v plus dv. This much clear? Velocity increases and some part going. This decrease of the mass is actually of the gas. So dm and along with this velocity vg. This much. So we have to take into account this part, or we can say this velocity is negative. We can take this part positive. So this will be dm into minus vg. We have taken this vg negative because if we take the velocity of the rocket as positive, we'll definitely take the velocity of gas negative because it is in opposite direction. So we have taken this as negative. So this is our equation from conservation of law of momentum, and we can name it as equation 1. Take a pause and copy it. Now mv equals to, now we have to multiply this, mv plus m dv minus v dm minus vg dm. Okay, this is our equation. Now one part I just make a correction, minus dm dv minus dm vg. Now see this part, as dm is very small and dv is also very small, very small, so the product of these two will be very small, and we can actually neglect this one as this part is very small. When we talk about a large thing, if very small portion is coming out, we can neglect. This is very interesting thing in physics, and this part can be neglected as this will not do no harm in my total equation, as this part is very small. If we take one glass of milk and we drink the whole glass, even though there is some milk will be left over, but we can say I have drunk all the milk, though some milk will be stick to the glass. So that is very small and can be neglected. This way this can be neglected. So ultimately the equation will be, now mb can be cancelled, so ultimately the equation will be m dv equals to, and that part also neglected, we can write v dm, this is from this one, and plus dm into vg. So these two negative part is there, and side change, and this part cancel, and this part also neglected. So this is left, or m dv equals to, dm can be taken as common, v plus vg. So this is equation number 2. Name it. May I take a pause in the video and you can note down. Okay, now I'm rubbing this part. Now the most interesting part you have to write, and this interesting part is, see, if u is the initial velocity of take the gas which is taken the initial velocity, and if I take the velocity relative velocity of the burned gas with respect to the rocket is going up and gas is coming down. Suppose this is velocity relative velocity will be negative of the difference. That means we can write the relative velocity as u will be minus v plus vg, because in opposite direction the velocity of rocket is v and velocity of gas is vg, so the relative velocity will be added up. So we can write this equation number 2 . This equation number 2 can be written as m dv equals to, now we can change v plus vg. This can be changed as negative of u, so u dm. We can write like this. Now dv equals to minus u dm by m. Clear? Any confusion? If there is any confusion, take a pause and review these equations. Now we have to calculate v. So v will be integration dv equals to integration minus u dm by m will be equals to minus u, we can take as common. Now integration dm by m, and what will be the limit? It is limit m naught to m. The limit of m, the range is m naught to m. Initially it was m naught. Now there is a formula, minus u. Now integration dm by m means log m. This is formula, and limit m naught to m. Now this is formula you have to remember. The formula is integration dx by x equals to log x. So we have used this equation. Okay. Now we can write minus u log m minus log m naught. This is upper limit minus lower limit. We have put this m, upper limit is m and lower limit is as m naught. So if I take minus inside, u equals to log m naught minus log m, because we have taken this minus here, so it will become positive plus, and here minus will come. So we have written in this way. And u, now there is a formula of log a minus log b means log a by b, that means m naught by m. So velocity is u log m naught by m. Okay. Now here if initial velocity is not 0, then also we can use limit here also. So if this is v naught to v, so here will be we can write here v naught to v minus v naught, or v equals to v naught plus this. So this is velocity of the rocket, and if we take initial velocity as 0, then this part will not there. So this is velocity of the rocket v after time t. Okay. Okay, so this is, we have find out the velocity of the rocket. So this is first part, and I will continue this video for as a second part of the this equation. Okay, thank you.